This video is all about solving non-homogeneous second-order differential equations. So here's a second-order differential equation, and it doesn't equal 0 anymore, it actually equals a function of x. Our approach to solving an equation like this involves 3 steps. We are first of all going to solve it as if it was a homogeneous second-order differential equation, just like we did last lesson. So I'm just going to make it equal to 0 to begin with, and solve it like we did last lesson, and that will give us what's called our complementary function. So that will give us one part of our solution. Then what we are going to do in the second step is we're going to solve when it actually equals f of x, and that will be called our particular integral. And the way that we will do that is we will choose an appropriate substitution based on whatever this f of x function is over here. So basically what I'm saying is we will look at whatever this function is, we will then guess some solution that's going to be similar to that, substitute it in over here, and then that will give us more information on what our particular integral will be exactly. And then our final step will be to add these two things together. That will give us our general solution at the end. We know that that's going to work because I know that the complementary function, which is the solution that we got from solving like we did last lesson, I know that when I differentiate that and substitute into the left-hand side over here, I get 0. The particular integral, I know that when I substitute that in over here, I get f of x. Therefore, when I add the two things together, I will get f of x as my solution. So, we're splitting this up into 3 stages. Complementary function, exactly what we did last lesson. I now need to talk to you about the particular integral and how we do that. So, what we do is we look at the left-hand side here, the f of x. Depending on that function, that tells me what to guess as my particular integral to substitute in on the left-hand side. So, if on the right-hand side here, if that was just a constant number, then I would guess my particular integral to just be a constant number. So if this was a constant number, whatever it might be, k, I would guess lambda as being a particular integral on the left-hand side and substitute that in to each of these, and that would tell me what lambda would have to be so that all of this would equal k. If it was linear on the right-hand side over here, then I would guess lambda x plus mu on the left-hand side over here. So notice the coefficients are not going to be the same here. On the right-hand side here, I would actually know what these coefficients would be over here. I would still guess lambda x plus mu, substituting that in here, here and here, and then by making all of that equal to the function, it will tell me what lambda and mu should be. It'll become a bit clearer when we look at an example in a minute. If it's a quadratic over here, then I would guess a quadratic over here. So I would guess my particular integral as being lambda x squared plus mu x plus nu, like that. If I have an exponential on the right-hand side over here, so k e to the px, then I would guess my particular integral as being lambda e to the px over here. And again, I would differentiate this to get this, differentiate it again to get this, substitute each of these in, and that will tell me what lambda has to be. What's on the inside would match whatever's on the inside of the exponential over here. If it was a trigonometric function, if over here was a cos, so it might look like m cos omega x, then I would guess my particular integral as being the sum of the two different trigonometric functions, and you do need to have them both. You need to have the cos and the sine. The coefficients, I would need to work out what they would be, but the omega on the inside, that would match up with the omega here. Similarly, if it was a sine or a combination of sine and cos, I'd still have the same particular integral. So, just to recap what I'm saying here is, I look to see what this function here is, and depending on what type of function it is, that tells me what to guess as my particular integral, what y should equal for me to substitute it in here, here and here. That will then, when I work it through, it will allow me to work out what these constants should be. Then I know what the particular integral will be. There is one little exception that you need to be careful about. The particular integral here must not match up with your solution from the complementary function. So we're always going to work this bit out first, like we did last lesson. If our particular integral does match up with something that we worked out for to be the complementary function, then what we would do is we would multiply our suggested particular integral by x. And I'll go through an example of that in a minute. So we're going to go two examples. So example 1 looks like this. So we want to solve the general equation to that differential equation. So step 1 is doing exactly what we did last lesson in finding the complementary function. So I've just made that equal to 0 now, rather than the 13 sine 3x. And like we did last time, I'm going to find the auxiliary equation. So m squared minus 5m plus 6. Solve that to work out my two values of m. I've got two distinct roots, so that allows me to write down my complementary function to this equation like that. Right, step 2, on to the new stuff. So we want to find the particular integral. Now, on the right hand side here, I've got a trigonometric function. I've got 13 sine 3x. So try and get these next to each other. So I've got 13 sine 3x. So that's telling me that omega has to be 3. So my guess at the particular integral is going to be lambda cos 3x plus mu sine 3x. That is my guess. There we go. That is my guess. That's my guess at the particular integral there. So I'm going to substitute this into this equation to try and work out what lambda and mu have to be. So I'm going to differentiate that. Just using the chain rule there, the cos 3y is going to differentiate to be minus 3 sine 3y. The sine 3y is going to differentiate to be 3 cos 3y. And then I'm going to differentiate that again to get that. So this is where it's going to get quite long because I need to substitute this in here. I need to substitute this in here and this in here and make it equal to 13 sine 3x. So if I substitute that in, I'm going to be going landscape now because it takes up quite a lot of working out here. So this is me substituting all of that in. This was the d2y by dx squared there, minus 5 lots of the dy by dx, plus 6 lots of the y equals the right hand side. Expanding these brackets out gives that. Collecting up the like terms, so I've just collected up all of the cos 3x's at the front and all of the sine 3x's here. And now what I can do is factorise out the cos 3x here and the sine 3x there. And that's useful because now I can compare what's on the left-hand side to what's on the right-hand side. Because I can see on the right-hand side there shouldn't be any causes, which tells me that all of this here has to equal 0. Similarly, I know all of this has got to equal 13. So we have simultaneous equations. And if I solve those simultaneous equations, that tells me the value of mu and the value of lambda. So now I know what my particular integral is. So now we get to our very last step of the question, where we can get our general solution, which will be our complementary function, which we worked out in step 1 of the problem here, and add it to the particular integral. This is your final solution. If you were to substitute all of that in to this, you would get this. Because we know that when we substitute this in, this will become 0. And I know that when I substitute the rest of it as well, when I do all the differentiation for this part as well, that will give me this part. Right, second example. We want to solve this differential equation. Now you'll notice on the on the left-hand side there, just to save some working out, that's actually the same left-hand side as in the previous example, which means that the very first step would be exactly the same. All this bit here would be exactly the same in this case. So straight away, I've just written down the complementary function as being exactly the same as what it did before, because the left-hand side's the same. Now, looking at the right-hand side over here, I've got the exponential. I've got e to the 2x. So if I've got e to the 2x, that would make me think that lambda e to the 2x would be my particular integral. But notice how that matches up with something in my complementary function, which is a big problem. If I substituted that in over here, I know that that's going to end up giving me 0, not e to the 2x. So I know that this isn't going to work. So what I do instead, like I was talking about down here, instead of having this as my particular integral, I'm going to times it by x and get that as my particular integral. I'm then going to go through the same steps. I'm going to substitute that in. So if I differentiate it once, so this is differentiating this using the product rule. So differentiate the lambda x, I get lambda times e to the 2x. Then differentiating the e to the 2x, I get 2e to the 2x times lambda, times 2 lambda. So that's differentiating that using the product rule. I then differentiate this again to get that. I am now going to substitute both of these in up here. So I've got all of this minus 5 lots of this plus 6 lots of this equals e to the 2x. Multiply out the brackets, collect up the like terms, and what we see here actually, I've got 2 lambda e to the 2x plus 2 lambda e to the 2x minus 5 lambda e to the 2x. So when I collect up those 3 terms, I get this. And then when I collect up these 3 terms, I actually get 0. So I'm just left with this equals e to the 2x. So therefore, I know that lambda is going to have to be minus 1. Now I know my particular integral. So now I can do the final step in getting the general solution, where I know that it will be my complementary function that I worked out before, plus my particular integral. So, key things, 3-step process. start off by doing exactly what we did last lesson, where we make it equal to 0 and you find the complementary function. Then you look at the f of x there, and depending on what it is, you take a guess at what the particular integral should look like. You then differentiate your particular integral twice so that you can substitute it into the original differential equation and figure out what your constants have to be. Then at the very end, you can just add your two answers together to get the general equation.